So today we're going to begin with a special triangle. Take a look at the image below. You might notice that it has the following properties. It has one angle that measures 90 degrees. So it has a 90-degree angle. And as a result, we would say that this is what we would commonly call a right triangle. You'll also notice that two of the sides are the same, which in turn also makes it into an isosceles triangle. Now, the property of an isosceles triangle is that not only are at least two of the sides the same, but these two angles are also going to be congruent to each other. Okay. Now, for the sake of just being able to introduce some new information, I'm going to say that this first angle up here, I'm going to call that angle alpha, and that's this symbol. And I'm going to say that this angle here is going to be referred to as beta. So just because we're going to be using some of this language later, these two happen to be Greek letters. The first one is called alpha, and the second one is called beta. These are two of the most common Greek letters used. And in mathematics, there's this habit of using Greek letters to explain or to determine angles within a shape. Okay. Now, given that this is an isosceles triangle and it's also a right triangle, we end up that both alpha and beta, these two angles, are going to be equal to 45 degrees. Okay. So as a result, we say that this is what we call a 45, 45, 90-degree triangle. Okay. So what we're going to do is we're going to see if we can figure out certain patterns based on this. So I'm going to go ahead and I'll say, what happens if I have my triangle and I say that this equals 1 and this equals 1? What is the measurement of the hypotenuse? So there's nothing magical about this problem. We are still dealing with the Pythagorean theorem. And so as a result, I'm going to say that I'm going to figure out the answer by applying the Pythagorean theorem. Which basically means I have a squared plus b squared equals c squared. I'm going to conveniently, I'm going to call this first one a, this one here b. It doesn't matter which one I select, it's just the same thing. But the hypotenuse is definitely c. And the hypotenuse for right now is basically unknown. Since a is 1, I just replace it. 1 squared is equal to c squared. This then turns into 1 plus 1, which turns into 2 is the same as c squared. Now, at this point in time, I will now say that I'll rewrite it here. And I'll take the square root of both sides. Given that 2 is a prime number, I know that I can't break it down, so that's my answer. So now I can conclude that the answer would be that c is in fact the square root of 2. Okay, so that is my answer at this point. So c is equal to the square root, which means I can go ahead and get rid of this, and I can easily replace it by the square root of 2. Okay. So the question becomes, because I'm trying to figure out a pattern, what happens if I then decide that I have kind of a triangle with the same characteristics, except that now I decide that my triangle, and let me draw it first. I decide that I have a triangle with very similar characteristics, but I decide that this now measures 2 and this measures 2. What is C in this case? Well, since I'm not sure what the answer will be yet, I'm still going to go ahead and just properly apply the Pythagorean theorem. So a squared plus b squared equals c squared. And I will end up saying that, let's call this a, and let's continue to call this b. So this turns into 2 squared plus 2 squared is equal to c squared, which becomes 4 plus 4. Together, that makes 8 c squared. I can actually break this apart. So c squared, take the square root of both sides. I know that this makes 2 times 4, where 2 is prime. I know that 4 is 2 times 2, bring down the original 2. And I quickly discovered that in here I have 2 of a kind. That means I can find the base. And so the base becomes 2 with a leftover of square root of 2. My conclusion, therefore, is that c must now be 2 times the square root of 2. So what I'm trying to figure out is whether or not there's a pattern here. So I'm not sure if I see it yet. So what I'll do is I'll work on a triangle that pretty much is the same. And I'll say, what if my triangle now looks like this? But I conveniently call that 3 and 3. Can I predict how much C will be this time? Now, personally, I am claiming that yes, you can predict it, but it depends on whether or not you see certain things. Okay? So I don't have anything else to use other than the Pythagorean theorem, so I'll rely on it. A squared plus b squared equals c squared. This now turns into 3 squared plus 3 squared is equal to c squared. This becomes 9 plus 9, which turns into 18. Okay. Because this is now c squared is equal to 18, I can go ahead and just solve it here on the side by taking the square root of both sides. I happen to know that 18 is the same thing as 2 times 9. Of course, 2 is prime. And 9 happens to be 3 times 3. Bring down the original 2. And I quickly realize that again, I have a perfect square with a base of 3. Let's rewrite it this way. and a leftover of square root of 2. So once again, it seems that there is in fact an actual pattern. Now, I compare that with the original, where it's just square root of 1, and I quickly realize that on the original one, the sides were originally 1. For the second one, the sides were originally 2. And for the third one, the sides are originally 3. So what that concludes is that in order for all of this to make sense, then that means that my original answer can probably also be rewritten like this. So I'll say or. I can rewrite it as 1 square root of 2. And that is also the value of c. In which case, I now have a pattern. Now, as a result of this particular pattern, I can now say so I'll start like this. For any 45, 45, 90-degree triangle, the hypotenuse is the product of the length of one side and square root of 2. What does this really mean? Well, as soon as I say the product, so I'm going to go over here and I say here, as soon as I say the product, I am automatically suggesting that I'm going to multiply. So I'll put that symbol in there. And so the question becomes, what is it that I'm multiplying? Well, I'm multiplying the length of one side and square root of 2. Okay. So with this in mind, I can now say, for example, if the length of one side of a 45, 45, 90-degree triangle is 6, then the hypotenuse is 6 times the square root of 2. Okay, so I'll be able to say if the length of one side of a 45, 45, 90-degree triangle is 6, then the hypotenuse is 6 square root of 2. And the picture would look something like this. I can imagine having a picture of a triangle, and it's a right triangle where this measures 6 and this measures 6. And as a result of my calculations, this will measure to 6 square root of 2. Furthermore, if I now have a triangle, I'm going to call it some general triangle, where the length of the side is measured as x, also a right triangle. I can now say that I happen to know that this is going to be the product of the length of one side, so the length of one side, doesn't matter which side, times the square root of 2. So this becomes the length of one side times the square root of 2. Think of this as my general solution. For special triangle, which in this case happens to be a 45, 45, 90-degree triangle. Okay. The second special triangle, that is something we're going to look at. So I'm going to call this special triangle 2. My second special triangle is going to be one that measures 30 degrees by 60 degrees by 90 degrees. We call that a 30, 60, 90 degree triangle. Now, the properties of that particular triangle are the following. First of all, we have one side that is longer than the other. So it is definitely not an isosceles triangle, but it is a right triangle. And the first property that should be understood is that if I take the shortest side, okay, the hypotenuse is always twice the size. In other words, if this side is 1, then this side is 2. Okay. So what's the measurement of the third side? Again, Pythagorean Theorem comes to the rescue. So I'm going to say that I have Pythagorean Theorem. And in this particular case, I'll have a squared plus b squared equals c squared. Let's call this A. Let's call the missing piece B. And of course, this is C. The hypotenuse is C. This turns into 1 squared plus b squared is equal to 2 squared. This becomes 1 plus b squared is equal to 4. In normal circumstances, I go ahead and I would add, but because 1 plus b squared doesn't give me anything I can use, the only thing I can do here is take away 1 from both sides. That leaves behind b squared is equal to 3. Therefore, if I do the square root of both sides, it turns out that b is in fact the square root of 3. And that becomes my answer. Now, because of what I'm about to do in a few minutes, I'm going to say that I can also say or b is equal to 1 times square root of 3. And pay special attention to that because I'm kind of recycling what I learned in the other example. So what happens if my triangle now looks like this? And I decide that this is going to measure, instead of measuring 1, the shortest side, what if I say this measures 2? Well, remember, the hypotenuse is twice the size, so this is automatically 4. So how much is this? The third side. Okay. I'll just plug it into my rule. A squared plus b squared equals c squared. Let's continue to call this a, this is c, and the missing piece is b. Okay. So let's continue to assume that that's what we have. That turns into 2 squared plus b squared equals 4 squared. Turns into 4 plus b squared is equal to 16. Take away 4, take away 4. I am left with b squared is equal to 12. B squared equals 12, square root of both sides. This turns into 3 times 4. I know 3 is prime. 2 is 4 is not, so this becomes 2 times 2. Keep the original 3. Like always, I'm looking for a perfect square, and I know the base. So the base is 2 times square root of 3. And conveniently, this is now the answer for B. Now, similarly to what I did with the other example, I can now predict what I think will happen for my next example. So for my next example, I'm going to say, suppose my triangle looks like this. My shorter side is 3. That automatically means that my longest side on the hypotenuse must be twice as much. That is 6. And I'm going to predict that the leftover section, which I've been calling B, will be 3 square root of 3. So then this is going to be my prediction. Okay, so I predict that my answer will be 3 square root of 3. All I can do with that is plug it into my formula. So a squared plus b squared equals c squared. I'll continue to call this a. This is still c. And this one can continue to be b. All right, so then that becomes 3 squared plus b squared is equal to 6 squared. That turns into 9 plus b squared is equal to 36. Subtract 9 from both sides. And b squared is going to be equal to, let's see here, 36, 35. 26, 27. And it turns out that if I square root both sides, 27 is in fact 3 times 9. 3 is prime. Make sure to include the square root symbol. And 9 is 3 times 3 with the original 3. Like always, I'm finding the perfect square. This has a base of 3. Times square root of 3. Which in fact matches my prediction. And this, of course, is the answer for B. As a result of all this, if I have some general triangle, (30, 60, 90), 90 degrees, it turns out that if this is x, this will be twice the size, and this will be the same as the original shorter side times the square root of 3. So this is going to represent what I call my general solution. For a 30, 60, 90-degree triangle. So I hope that made sense. These are the basic notes for this section. Okay. As always, you can send me an email letting me know any questions that you may have. But that will be all for now. Thanks.